Okay, so if you're given a curve through a set of parametric equations like these at the bottom there, you're supposed to be able to do something with it. And one of the first things that you learn to do in calculus is finding tangent lines. So let's say you were given a curve such as this one, and you want to find the tangent line to this curve at a specific point. And this time I'm giving the point as the t value. So you can think about this as the time instant, right? The point in time at which you want to find the tangent line of the curve at. And the idea for this formula right here, we're going to be using that one. You always can just memorize it. That's always a choice, but I think it's helpful to understand why it is what it is. And if you remember the chain rule, from the chain rule, if you were trying to find the derivative of y with respect to t, so that is, remember, y is given to you as a function of t right here, right? So t to the power 4 plus t. You can always just use the chain rule. So this here on the left would be y prime. But you can always just use the chain rule and say that this is dy dx times dx dt. So this dy dx would be you taking the derivative of y when x is the variable, and this is you taking the derivative of x when t is the variable. The reason why, one of the ways to remember the chain rule is to sort of pretend like these cancel, and canceling the dx's gives you the dy over the t again, which is what you have on the left. And now by just taking this dx over dt over to the left side, dividing, because it's multiplying here on that side, you get this formula here. So I think it's kind of helpful to remember what is the correct formula. From this point on, though, to save a little bit of time, I'm not going to be writing dy over dt every time and dx over dt every time. I'm going to come to an agreement with you to say that y prime is dy over dt and x prime is dx over dt. Just for us to save a little time, this is an agreement that we make from this point on whenever we're dealing with parametric curves. Now, this is one of the easiest types of problems that I can ask you to solve. For example, your teacher can ask you to solve. If you want to find dy over dx, right here, you could just do dy over dt over dx over dt as long as the bottom here of this fraction is not 0. And so right now this will be, go again, dy over dt should be just a direct use of the power rule for t cubed plus 1, all of that divided by, and then dx over dt is going to be 3t squared. So this is dy over dx. So this is the derivative of y with respect to x. Even though we have no x's in here, this is what it is. And then I can go ahead and plug in t equals to -1 to find that this is going to be 4 times -1 cubed plus 1 over 3 times -1 squared. So this is going to be -4 plus 1 over 3 positive, and this is going to be -3 over 3, which is -1. So that is the derivative of y with respect to x. That equals -1 at this particular point. This should be the slope of the tangent line that I want at this particular point. And so if I remember that I know what the point slope equation of the line is, like this, y minus y1 equals m times x minus x1, I've found m. M is -1 right now. Okay, so that means m is -1, but I still have to find these two values, y1 and x1, and these are going to be the values, just the values of x and y at this particular point, but you can just always just plug in x equals t cubed plus 1 at t equals -1. So you can get -1 cubed plus 1. That will be -1 plus 1 that will be 0. And you can find, so this is going to be your x1 actually, and your y1 actually, the coordinate of the point at that particular moment. And then y will be minus 1 to the power 4 plus minus 1, right? Because I'm taking -1 and plugging it into here. And this then will give me 1 minus 1, which will also be 0. So that means my line goes exactly through the point 0, 0. So these are the two values that I need to plug in. My equation then becomes y minus 0 equals -1 times x minus 0. So it's just x equals y equals -x, excuse me. So this is the equation of the tangent line at that point. And this is excellent right now. But sometimes, so you can pause here, make sure they understand everything. This is not the most complicated that it could get. This is, on the contrary, the easiest that it could get, I think. It could get a little bit more complicated, though, if you're solving a problem such as this one, which is a problem where you're supposed to be able to, looking at this, be able to find t first and then do everything that we did in the previous example. So the first example just gave us the t value, and we had to use t, remember, to find x1 and y1, right? But right now we're not given the t value, we're given x1 and y1. So in this problem, the point that was specified to us had x1 equals 15 and y1 equals 2. And so I need to find t to be able to plug it into the dy over dx equation to find the slope of the line, right? So, of course, I know that at that particular moment in time, when the point is right here, I'm going to plug that t value in here, do t squared plus 2t, and that's going to have to give me 15. So by that logic, I'm going to have 15 equals t squared plus 2t. And so t squared plus 2t minus 15 should equal 0, and that will allow me to find t, right? By just noting that plugging the t that I want into this equation will give me 15 for x. Of course, I could have done the same for y if I wanted to, but I can see right here that y has a 2 to the power t and a 2t. That's a little bit of a more complicated equation to solve than this first one, which I can solve either by factoring or by using the quadratic formula. This one is not too hard to factor. You can see that you need two values that, when multiplied, give you -15. So they're going to have different signs. And when added, they're going to give you +2. So the positive is going to be the largest of the two values. And so 5 times 3 comes to mind. T plus 5, t minus 3, I think works pretty nicely. And so you do 5 times -3 gives -15 check, and then 5 plus -3 gives me +2. So this is the correct location here for my curve, and I should then get t equals -5 or t equals 3. I'm going to take this t value and plug it into the equation of my tangent line. There is a problem here, of course, and the obvious problem is that I have two t values, as I've said, and my curve does not go through this point twice. If you look at it real quick from the graph that we were given by the problem, the curve only goes through this point once, right? This point right here is a point that the curve goes through twice, but not the one that we're looking at. And the reason for that is because when I set x to equal 15, I'm actually calculating the intersection of the curve with this line. This is the line x equal to 15. So there are two different points that the curve goes through. And so I have no other choice but to check to see if one of those is going to give me the correct y. Y is the only discerning variable here. You see that when t equals -5, will I get y equals 2. When t equals 3, will I get y equals 2? And that's going to give me my correct answer here. So I'm going to say t equals to -5. And then y is going to be 2 to the power -5 plus 2 times -5. This is going to be 1 over 2 to the power 5 plus 10. 1 over 2 to the power 5 is going to be a small number, positive, that I add to 10. It's going to be over 10. It's not going to be over here. Or I should say it's going to be all the way up here. It's not going to be down here near 2. So it has to be at t equals 3. I'll check it anyways, just for completion here, so you know what to do. When t equals 3, this will be y equals 2 cubed. Again, plugging this back into this equation that we have. Y equals 2 to the power t minus 2t, so 2 to the power 3 minus 2 times 3. And this will be y equals 8 minus 6, which is 2, which is what it's supposed to be. So we are able now to throw away the first t value of -5, and then use that t is equal to 3. Now, with this, I can go back and, from the point slope equation of my line, I know that I knew from the beginning that x1 was 15 and y1 was 2. What's left for me to find is the m, the slope of the line, dy over dx, and from the formula that we just introduced, dy over dx will be y prime over x prime. Remember, the y prime we agreed is dy over dt, and x prime is dx over dt, and so I just take the x and I derive it as, this is going to be 2t plus 2, and then I derive y prime. Some of my students can't quite remember what's the derivative of 2 to the power t. Usually they know what's the derivative of e to the power t, and that's just e to the power t. But if you happen to forget what's the derivative of 2 to the power t, you can remember that 2 is the same as e to the power natural log of 2. So by raising it to the power t and then taking the derivative, all you're doing is you're taking e to the power t times the natural log of 2. And with a quick use of the chain rule, you can see by calling this on the top here u, this is e to the power u again, times the ln of 2, which will be your u prime, from the chain rule. And so this here turns back. If you retrace your steps, this is going to turn back into 2 to the power t. So this is going to be 2 to the power t times the ln of 2. So this is 2 to the power t times the natural log of 2 minus 2. This is easy to derive, right? So these are the two values that I need to put in my fraction. This is y prime over x prime, 2 to the power t times natural log 2 minus 2. All of that over, if I go back, 2t plus 2. So now this is easy for me to find as long as I remember that t equals 3 right here. So when t equals 3, this is going to be what? 2 cubed times the natural log of 2 minus 2, all of that over 6 plus 2, which is 8. So the top will be for me 8 natural log 2 minus 2 over 8. It is what it is. The natural log of 2 is not a number that I can handle without a calculator, but it is a number nevertheless. And this is the value of m. This is the slope of my line. So I can go back and turn this into y minus 2 equals 8 natural log 2 minus 2, all that over 8 times x minus 15. And now, of course, I could expand this and make it into slope-intercept form, but I'll go back to the problem and see if that's what the problem wants. Does the problem want the equation in slope-intercept form or not? The problem didn't even want the entire equation, just wanted the slope. So I didn't have to actually go ahead and write this in black right here. The answer was just that. Okay, so I'm going to stop right here, and I hope you're able to understand what I did.